So today we hope to finish this chapter. We are still at the analog input and output. So last week we have learned how the analog input is converted to digital data so that we can process the analog input in the microprocessor or microcontroller, because our microcontroller is the digital device, so that we need to convert any analog input that we want to process to the digital first before we can process. And we have learned the theory regarding the analog to digital converter, the ADC, how it convert the analog voltage into the digital representation. And today we will look at the reverse operation, which is the DAC, digital to analog conversion, right, or analog output at the microcontroller. And we also will look at what is called the pulse width modulation, or PWM, and we will look at the modular programming techniques. Yeah, this is the equation to convert any analog voltage into a digital representation, where Vin is the analog voltage over VER, which is the V reference of the ADC. And 2 power of n, where n is the size of the ADC. Yeah, so if the ADC is 3-bit, so the size will be 2 power of 3, which is 8 which is 8-digit binary number, right? So if our ADC is 8-bit, so we will have 2 power of 8, which is 256 representation, yeah, digital representation. We have learned also what is a quantization error, the greatest quantization error, which is half of the step size, yeah. And we also learn what is sampling frequency and Nyquist sampling criterion, where this one is very important to avoid what we call the aliasing, to preserve the information such that the information is not totally lost when we convert from analog to digital. And we have learned how to use the ADC in the embedded microcontroller, yeah, where we have 6 input, analog input. P15 to P20 is the analog input for this embedded microcontroller, and we have 1 analog output, which is P18, right, where we can convert from digital data, digital representation, into the analog voltage through this pin. This is the example of the analog sensor, the temperature sensor LM35, where we can use to sense the temperature of the environment, and we can use the embedded microcontroller to read that temperature, where this sensor we convert the temperature to analog voltage, and we can read that analog voltage using our microcontroller and convert to digital, and we can process that data in our microcontroller, and we can write the program to process the analog data that we we receive from the sensor. And one thing to remember is that the analog in function that we use in embed is normalized from 0 to 1. That means that the minimum value is 0 and the maximum value is 1 when we read the analog value from this analog in function, right? So we use analog in function here, right, to read the pin, analog pin, to the variable, yeah, to the variable. So for example, in this case, the variable is voltage. So here we read the analog input pin P19 that we name it POT1 here. So here we read port 1 dot read, yeah, and this value is normalized from 0 to 1, yeah, this value. And to get the actual value of the voltage, we need to multiply by 3.3 because our reference voltage is 3.3, right? So this is to get the actual value of the voltage by using this analog in API or function, right? Once we get the voltage value, then we can easily write the program to test the value. Right? For example, if the voltage is more than 0.35, in this case, means that it is 35 degrees Celsius. Yeah, because we learned already that in LM35, the uh, output is or the sensitivity is 10 millivolt per degree Celsius, where 1 degree Celsius represent 10 millivolt. So 0.35 volt means that uh, 35 degrees Celsius. We multiply by 100 here, we get 35 degrees Celsius. So if more than 35 degrees Celsius means that we said here is for to indicate that the temperature is hot. And if it is less than 0.2 volt, or in this case is 20 degree, so it means that it is cold. But if within the range, means that within 35 and 20, so the temperature is okay. And we have a wait function here before we go back to read again and uh, and change the output here depend on the temperature that we read. So this is exactly based on this flowchart. This is how we display the value on the computer screen. All right, we used another API function, serial function, right? And this is how we name it: USB TX and USB RX. So this is default. So the name we name it PC, and when we do this, we can use the function printf in C programming to print this to the on the monitor screen, right? So we can have the voltage, temperature on the screen. Okay, so to do this, you need to install the uh, one software, right, in order to display the data from the serial port or the USB. So in this case is you can use embed. The name is Term. So you can go to the embed website and download from the web page. Yeah, so this is the Term. You just install this. So this will include the driver and the driver to detect the your embed microcontroller. So it is something like this, yeah. If I can have the my microcontroller connected to the PC now. So I just connected my microcontroller to the PC. So for example, I want to yeah, we will use the embed online compiler for writing our code and compile our code. So for example, if I have the program here and I use the serial PC and I compile my program. This is so if we have the syntax error is like this, so it will give you the syntax error just like the any other compiler. Yeah, when you compile and you have the error, it will show that error in the output window, and you can know that this is undefined or syntax error. So just remove this, compile, and when you compile, it will save to your embed board. So this is the previous program that I saved to the embed board. But if we use the board that we get from this, yeah, this is another board or another microcontroller, but it's using the ARM architecture also, which is this one is the Nucleo or the ST, yeah, the microcontroller from the ST microelectronic. This one, when you want to save, it will not shown in the in this. It's a little bit different where when you copy to the file to the microcontroller, it will not shown here, but the program is directly go to the microprocessor memory. All right, it is directly programmed. This one you need to save for embed LPC 1768. You need to save into the flash memory of the microcontroller, and you need to press the reset button in order to program the microcontroller. So in this case, so I want to program, I just save this file to, I want to use the same name here. So just replace the previous one. Now it is already in my microcontroller, and I can actually yeah, I think I better use the another one where I have the analog input. Okay. So in order to run this is the Teratem, right? So when you launch the Teratem, you need to set the serial port that you connect to the microcontroller. In this case, is embed serial port. All right, this is the visual serial port. Just click this and click OK. So you will have this. Yeah, this is the temperature. So this is not reading from the LM35. Yeah, I use the variable resistor to provide the voltage to the ADC because I don't have the LM35. So if I vary the variable resistor, we can see that the temperature is now drop here. I try to make it smaller and smaller and smaller, so we can see here. So this is how we display this into this terratum, or display on the computer screen, all right, from the data from the microcontroller. And of course, you can use any other software that can read and display data from the serial port or the USB. So it can be anything, but I recommend this because it is from the embed. Yeah. And the next is the applying averaging to reduce noise. This is how we try to make the reading more stable, because if we can see here, although I not worrying the resistor, you can see that the reading is not stable. Sometimes you have 8 point something, sometimes you have 7, 8, and the value is not stable. I mean, it go up and down in small range, plus about 0.5 degrees Celsius. All right, because if we look at the uh, voltage, the analog voltage, it is not actually constant. Yeah, same as when you read from the LM35 sensor, the value that you read, the voltage that you get is actually not ideally constant. It is go up a little bit and down a little bit. So sometimes if you want more smooth reading, you can apply averaging. What is applying averaging? Means that it is actually to average the reading, yeah, get the average from the reading. So for example, if we have many readings, yeah, just like this. So what we do is we take 10 reading or more than that, or any number. Uh, the more the better, right? And we get the average value. For example, our reading is when we use, okay, so let's example, if our reading is 7.5, 7.8, 7.4, 8.0, or 8, and it's something like this, and this is repeated, right? So this is the reading. So what we do is that we take this, let's say this is number of reading until 16. Let's say we have until 20. So for example, these are the reading, right? These are the reading, and this is number of reading. So what we do is we have 10 time reading here, and we take the average, where we get the average. This is how we get the average, right? We sum all of this and we have this divide by 10. So this is the average value for the first one. And again, here we take the average, the next 10 reading, and and the next reading will be this is the next average, and we can see that here the value is not much different, right? 7.67, 7.68. So it looks more stable now as compared to 7.5, 7.8, 7.4, 8, and more. So we can see that we can make it more stable by average the reading. So if we take more value, all right, for example, 100, and we have one average, so the value will more stable in at the output, right? That is meant by applying average. So we can do that in programming by using the for loop. So this is how, yeah, we have I equal to 1 until I equal to 10, and we read the value, the analog, into the voltage, all right? And this is the total, right? We get the total here where we increase the voltage that we read, we plus to this average volt, yeah. And when we want to display, we take this value and divide by how many times we have added here. So in this case is 10, just like this, right? We divide by 10 and multiply by 100 because we want to display the temperature, right? Because remember LM35 is the output in temperature must be multiplied by 100 to get the temperature value. So uh, so this is the average temperature value, right? So it is easy. So in your project, if you want to apply the average so that the output is more stable, so you can use this method. Now the next one is digital to analog conversion. So this is how we convert the analog, the digital data into analog voltage. So the process is actually a reverse process from the ADC, where now we have the digital data from the microcontroller, we have the DAC, also built-in circuit in the embedded microcontroller, and we have the analog output here. And of course, we need to have the reference voltage. In our case, the embedded microcontroller, the reference voltage is 3.3 volt. And this is the equation to get the analog output when we have the digital data. So the V out is equal to D, the digital data from here, divided by the size, no, 2 power of the size of your micro controller, the ADC of your microcontroller, multiplied by the VR. So this is a rearrangement of the previous equation that we have in this in ADC, right? So instead of looking for D, now we look at this P. So if you rearrange this equation, so you can get this equation. This is straightforward. So for example, if uh, let's look at this. So the formula is P of equal to D over 2 power of n multiplied by V R. So this is the equation. And let's say our microcontroller is 8-bit. And the digital value is, let's for example, is in decimal is 200, right? So this is in the decimal, yeah, and we can get the V out equal to 200 over 2 power of n is 2 power of 8, which is 256, multiplied by let's, for example, our V out is 5 volt, yeah, so we have V out equal to we can use the calculator, right? So 200 over 256 multiplied by 5, so it should be 3.9 volt. And if the number is maximum, which is 255 actually, because remember this is the full equation is you have -1, yeah, but to make it more easier we just ignore this. So if we have 255, so we can have the maximum is 255, so we have approximately 5 volt, right? So that is how we calculate the V out, or estimate the V out using this equation. This is straightforward, very easy. And when we plot the graph in voltage, this is the voltage and versus the digital value. All right, output voltage, the digital value, we can have something like this, right? So this is when this is the size is 3 bit like this, so 0 we have 1 here, so this is 2 power of 3 VR, 2 power of 3, this is 8, yeah. So for example our VR is 8, so we have 1, and here the next one here until we have the maximum 1. So this is the same as this example, with different value. For example, the LPC, our microcontroller, which is the 10-bit DAC, right? Our ADC also 10-bit, and the DAC is also 10-bit. Hold on, the ADC of in our case is 12-bit, not 10-bit. Sorry, the ADC is 10-bit, yeah, but the DAC is 12-bit. The ADC is 12-bit in our case, but the DAC is 10-bit. Right. So when we want to calculate the V out for this is to calculate the step size. Right, V out over the maximum 10-bit is 1024. So the step size is 3.22 millivolt. Yeah, in this case the step size is 1. So for our microcontroller the step size is 3.22, right? Because it is 10-bit, this is 8-bit, sorry, this is 3-bit. So of course if we have more bit, yeah, the size is bigger, so our step size is smaller, and this is better, right? The bigger you have, the better the result. And this is how we output the analog voltage at the P18 pin. P18. We have only one analog input here, which is P18, and we can use analog out API. So for example, we want to output the analog voltage to through the pin, P18 pin. So let's say we name that output as A out. Yeah, of course, must be P18. So A out equal to 0.5. Automatically, the microcontroller will give you 0.25. Remember, it is normalized value also, so we need to multiply with 3.3. So we have 0.825 volt. If we write A out equal to 0.25. If we write A out equal to 1, so we will have 3.3 volt. If we have A out equal to 0, we will have 0 volt. If we have A out equal to 0.5, so you multiply with this 3.3, you get 1.65, and so on, right? So this is very simple. So from that, right, if we draw this actually in okay, actually we can draw this, right? If we draw, this is V and this is time. Okay, so we want this. So at first our output is 0.8 at time 0. This one should be at time 0, 0.825. So let's, for example, this is 1 volt. No, this is 3.3 volt. This is 2. This is 1. So at time 0, this is time 1, 2, 3, 4, 5, 6. So at time 0, we have 0.8 volt. So this is the value, not 1, but at time 0. And at time after 2 seconds, the output is 1.6 or 1.7 around this. And at time 4, yeah, after another 2 seconds, the value is 2.475 or 2.5 around this. So we can see that the voltage is like the staircase, right? This is increased by step. So we can create from that approach, we can create the sawtooth waveform by using this approach. But we can make it better by using the for loop, right? So in this case, we have for I equal to 0, I less than 1. We increase I by 0.1, and we wait every 0.01 or 1 millisecond, and we get the A out here, and we increase every 0.01 millisecond or 1 millisecond. So in this case, we will have something like this, where we have every 1 millisecond. So let's, for example, this is 1 millisecond, 2 millisecond, 3, 4, 5, 6, 7, 8, 9, until 10 millisecond. And we increase by 0.1, right? Voltage is, for example, this is 0.1, this is 0.2, 0.3, 0.4, and so on. All right. So at time 0, we start from 0. At time 0, we start from 0. Next, another 1 millisecond, we increase by 1. Next, increase by 0.1 until we have 0.9, because this is I less than 1, right? So the maximum will be 0.9. So we will have three sawtooths like this, right? Until the maximum here 0.9, and go back to 0, and we start again, right? Because this is in the while loop here, so it will repeated. So we will have the output like this on the oscilloscope, right? We have how many steps? 1, 2, 3, 4, 5, 6, 7, 8, 9 steps. Go back again. So exactly, we have 9 steps here to go back again, right? And we also can create the sine wave like this, yeah, from our microcontroller using the analog out, the ADC, right? But this one I don't have the code, yeah. So this one is uh, for you to go back and figure out how to get the sine wave from using the code like this, using the ADC, the, the the analog out function, right? So we can create the sine wave, and yeah, which is a good feature to have, right, to create any analog voltage that we want, right? So that will be the DAC, digital to analog converter. So you may need to use in your project. So depend on what is the application that you want to propose. So the next one is the what is called the pulse width modulation. So this is another features that very important in a microcontroller, where we use the pulse. Yeah, pulse is very simple signal in electronic, right? So a pulse is just a square wave like this, right? But this one, this pulse is or can be applied to many applications. Especially we can use the width. This we call the width of the pulse. Yeah. So we can use the width of the square wave or the pulse here to uh, to control other electronic devices. So we call that technique as PWM, or pulse width modulation. All right. So for example, if we connect our LED to a microcontroller like this, and we apply the pulse to the LED. So if our pulse is like this, this LED will be very bright. Yeah? So for example, if we scale the brightness of the LED from 0 to 10, so if we apply this pulse in this line as the input to the LED, so the brightness is, let's say, 9 out of 10. But if we reduce the width of the pulse, let's say, like uh, this T is equal to this T, right? Means that we on and off at uh, at the same time, at the same duration. So the brightness of the LED, and remember this one is the frequency of the pulse is quite high. We need to set to high in 10 kilohertz, 1 kilohertz or more, so that we can see the effect. Right? If too slow, we can see only the LED is on and off. Right? So if the frequency is high, so we can see that the brightness of the LED is now less to reduced to, for example, in the scale of 0 to 10 is now 5 only, right? Half of the full brightness. And if we reduce more, such that the pulse is like this, now the brightness of LED may be 2, right? So it is quite uh, dim now. So we can see that we can use the pulse to control the brightness of the LED in this case. And we also can use this pulse to control many other applications or devices. For example, the speed of the motor, the DC motor, that we will see later on, and maybe other electronic devices, right? So that is how we use the pulse uh, to to control our other electronic devices in electronic design. And in the microcontroller, actually, we can create this pulse very easily using programming, right? Using software, where we can just write the software to create the pulse. So, for example, to have the pulse like this, where the on time, the duration for high and the duration for low is the same, or we can call this the parameter that that represent this is called the duty cycle, which is a very important parameter in pulse width modulation of PWM, right? So if the time for on and the time for off is the same, we say that the duty cycle is 50%, right? So the duty cycle is actually simply the on time or the duration of high over the full cycle, the time for a full cycle multiplied by 100%, right? So this is called the pulse with 50% duty cycle, and we can create the pulse with 50% duty cycle very easily in program, right? So in our code, we can just have, so we have infinite loop here, and for example, the name of the of our pulse is digital out pin is we name it PWM. So we can set PWM to 1, and for example, the delay is with we can have in millisecond, yeah, 10 millisecond, and PWM to 0 with 10, and done. So this will create the pulse with t equal to 10 millisecond, t equal to 10 millisecond here, where the full cycle is 20 millisecond. All right, so we get 50% duty cycle. So you can see we can create easily, yeah, in software or in program. We can also change the duty cycle. For example, we want more duty cycle. For example, we want to have something like this, where this is 13 or 15 millisecond, and this one is only 5 millisecond. All right, so we can have 15 here and 5 here. So okay, we can get this, and we have the same frequency, which is still, or same cycle, which is in 20 millisecond, but with different duty cycle, right? So we can create the PWM signal easily using software, but the problem is when we use the program to create the PWM, the problem is that we is now use all of the microprocessor resources just to create the PWM signal. So now we can see that we cannot use the microcontroller to do other things, all right? Because if you have other operation here, you can see that you are now will not get this anymore, because your microcontroller need to do this. For example, this take 1 millisecond, this one take another 1 millisecond, this one another take 1 millisecond. So your signal here is not 15 millisecond and 5 millisecond anymore, because it will plus this value. Now the thing, your signal here will be 5 plus 3, which is 8 millisecond, right? Because you have extra operation. So you will not have 20 millisecond anymore. This is not good, because when we create the PWM using the program or the software, we will not have any CPU time or CPU resources to do other things. So that is why the modern microcontroller or microprocessor will provide what is called the hardware PWM, where we can generate the PWM signal independently from the program. So instead of generating the PWM signal using the software, now we have the PWM hardware, where this one, when we turn it on, it will give you the PWM signal without using this programming code. All right, so that you can use your microcontroller to do something else, and let the hardware to generate this signal uh, automatically or independently. So that is why uh, we have the PWM. Where is it? Here at the pin, from pin P21 to pin 26. So you can generate the PWM signal without creating it using software. But by using software, actually you can use any of the digital pin here to create the PWM signal. But by using hardware, you need to use only this six PWM pins to generate the PWM signal, P21 to P26, right? So for the PWM signal, yes, we call this part as the period of the PWM signal, and this is what we call the on time, and the duty cycle is calculated based on on time over a period multiplied by 100%. In embed microcontroller, to generate the PWM output is very easy, straightforward. We use PWM out, and we can set the frequency or cycle of the PWM and the uh, duty cycle of the PWM using a PWM out function. So let's look at this example. So this is how we create the PWM signal in embed microcontroller. So in this case, PWM out is named as PWM1, and this is from P21, pin P21. So to create the PWM signal is straightforward using the embed API. If you don't have embed API, for example, in previous example where we don't use the API, the process is quite complicated, where we need to have the control register that is used to to do the setting to create the PWM signal. But by using the API, the embed API, so we can use this function straight away, PWM out, and to create the period is this PWM1, name of PWM. So this can be any name, remember. So in this case, the name is PWM1 dot period, and in the bracket here is set to 0.10, or is it set to 10 millisecond, right? Or you can have period underscore ms 10, means that in millisecond. So yeah, period can be in second, in millisecond, and also can be in the microsecond. And to set the duty cycle is very easy. For example, to set for 50% duty cycle is this PWM1 equal to 0.5, means that this is 50%. If you write 0.2, this is 20%. If you write 0.8, means 80%. If you write 1, means that the duty cycle is 100%. 100% means that the signal is constant. Yeah. Okay, so here we can use also this way, PWM1 dot write 0.5, also the same, or we can use PWM1 dot pulse width ms5, also the same, right? So we have option. So the easiest one is to use this option. So this is the output of this code. So you will have the constant pulse, constant cycle, and with constant duty cycle, which is 50%, where on time and off time is the same, right? This is from this code. And we can have something like this, where we can change the duty cycle of the PWM signal that we created. So this is using for loop, where we vary the PWM signal from 0 to 9, right? From 0 to 9, and we increase every 0.2, 0.02, and after 0.2 second, we go to this again, from maximum, we go to the minimum. This is from minimum to the maximum. So the output will be something like this. This is from the oscilloscope. So from the minimum, we go to maximum, and from the maximum, we go to minimum. Right, so this is the output from this code. And if we connect this output to the LED, so we will see the LED, the brightness of LED will change from very dim to very bright, and from bright to very dim. So actually we can see, if I can show you the all right, but before that, maybe we have a 5-minute breaks before we come back and continue our class. Okay, any question?
No, doctor, no question.
Okay, so we have a short break, and After that, I will show you. I will try to have my LED connected to my microcontroller and show you the output of the LED when we use this. Yeah. Okay. Now I have this program. Yeah. Now I transferred to the embed compiler, the online embed compiler, and here's the program. I just modified the wait time here so that is faster as compared to the previous one, so that we can see the effect of this program clearly. So so if I can show you the output of this, yeah, can you see? This is the microcontroller. This is the uh, this is the LED. You can see it is bright, very bright here, and dim and bright again. Okay, so that is can you see this on the screen?
Cannot.
Yeah. So that is how we have this, yeah, in yeah, in the microcontroller. So that is one of the application of the microcontroller. I want to show you another example where we can create more PWM signal in in our program or in our application. So this is another program where I use or I create two PWM signal with the same period and same duty cycle, right? Yeah. Uh, and let's see uh, the output of this. Yeah, I don't have in the slide, so I show you the screen of the oscilloscope for this. So I need to have a connection here, which is P21, P22. So I need to switch on my oscilloscope, and I need to have the connection. Not this one. Okay, so let's have this. So I need to compile the program and download to the embed. And let's open my oscilloscope. Okay, I have two PWM signal now. Can you see this on the screen? So this is how we create two PWM signal with the same frequency and the same duty cycle. So for example, we want to change the duty cycle of the second PWM signal. So of course, we need to have the here is different. So for example, we have different duty cycle. Here is 30%, 80% for PWM2. Right, when I reset my microcontroller, so I have this is the second one, PWM2. So the duty cycle is now 80% more than this one. This is number, yeah, this is PWM number one. So you can make your program to be more flexible, where you can receive input from outside, for example, to change the PWM signal, for example, the sensor, from the sensor, right? It's something like this. So for example, you have your microcontroller, and this is the output P21, for example, the PWM output, and you have the input or voltage, yeah, analog voltage, or maybe digital input also can. So for example, the input digital 4-bit, yeah, if 0, so the PWM duty cycle is 0%, for example. If you increase to 10, right, the input is 10, so the duty cycle is increased to 10, right, until you have the maximum one. Maybe the duty cycle is increased to, yeah, it depends on how you relate, yeah, the input and the output. So you can write the program, yeah, to read the input and change your PWM output, yeah, PWM duty cycle, right? So you can apply in your project as well, this PWM. So let's look at another application, which is a practical application of the PWM. The first one is to control the servo motor. All right. So a servo is a small rotary position control device. So it is a motor that can use to control the position of the rotator, right? Uh, for example, the radio control car, yeah, the RC car, right? Because the wheel of the car is actually controlled by the servo motor, yeah, because you can see the position, whether the position is straight, whether the position is like this, where you go, we want to turn right and turn left and so on. So it's depend on servo control actually. Steering, elevators, rudders, this is ship rudders to control the ship. So it is popular in robotic application, yeah, where we use the PWM signal to set the position of the servo. Yeah? So for example, This is the PWM signal, and this duty cycle of the PWM signal will represent the position of the servo motor. So for example, in this case, yeah, if we have 1.25 millisecond, yeah, the on time for the PWM signal is 1.25 millisecond. So the motor will at the 0 degree, and when we increase the on time to 1.5 millisecond, it will be 90 degrees. If we have 1.75 millisecond, we have 180 degrees, and we add more 2 millisecond, we will have 220 degrees, and so on. So that is how we uh, control the servo motor. Yeah. So this is how we connect the servo motor to the microcontroller. So we can use any one from P21. We have this one is P21 to P26. So in this case, we use P22, yeah, for the PWM input. And of course, the motor, when you use the motor, you need external supply, yeah, to supply the voltage and current to your motor. You cannot use the microcontroller to supply the current and voltage power to your motor, because motor normally need high current, right? But the microcontroller only has a very small current, yeah, in milliamp. But the motor need more current, so you need to have external power supply, external battery or external supply for your motor. And this is how we connect to the DC motor. For example, we have two motor here connected to the robot, for example, right? Where we have two wheels, and we use the motor driver. So this is the DC motor driver, yeah, the L293D, uh, which is the IC. We call it the motor driver, where again this motor need to supply with external supply, yeah, instead of using the supply from the microcontroller. So the microcontroller just provide the PWM signal. So this one is the PWM. We use two PWM to control the speed of the motor. So this PWM signal is connected to the enable pin at the driver chip here. Enable 1 for the motor 1, enable 2 for the motor 2. And we have this one is to control the direction of the motor. So for example, if this one is 1, this is 0, so the direction, the motor will turn at clockwise rotation. But if it is 1, it will turn at anti-clockwise rotation, right? Same as this one. So this is how we control the motor using a microcontroller, right? We have the direction control here, and the speed control is using the PWM signal. And of course, in this case, you need two PWM output, right? So just like in this example, right? This is how we create two PWM signal for the motor, like this. And for example, we want to increase the speed of this motor and this motor, and we want to have the same speed, for example, right? And same direction. So it should be the input for this one should be the same, 0 1 0 1 here, so same direction. And to get the same speed for both motor, must we must set the PWM duty cycle to be the same, and of course the frequency or the cycle must be the same. right? For example, 50%, both are 50%, so the motor will run at the same speed. But if we reduce, for example, we reduce the duty cycle for this one, so this one will move slower as compared to this one. So if you connect or you use this, yeah, to uh, to apply in robot application. For example, you have a simple robot, like this. This is the top view of the robot, and we have the wheel at the size at the side of the robot. This is the wheel. This is the wheel, the second wheel, and this wheel, of course, connected to the motor, the DC motor. DC motor. This is the view from the top. Yeah, this is motor. And at front of this we have the free wheel field rotation wheel, which is not controlled by a motor, right? Just uh, to make the robot stable, right? So to move the robot forward, so we just need to on these two motor and with the same speed, right? So for example, we go for maximum speed, so the PWM for the first one is 90% or more than that. So let's say we just allow for 90%. So both is 90%. So it will move at the same speed, right? But for example, we want to turn the robot to the right. We can have uh, another motor, a servo motor that control this wheel. All right, but let's say this one is not connected to any motor, which is just a free wheel, right? So what we can do is that we can use these two motors, two wheels. So for example, we slow down the speed of this motor so that we have uh, instead of 90, now we reduce to 70%. So the right wheel will move slower, and this one is faster. Of course, your robot will turn to the right? Because this one is slower compared to this one. So it will move the robot to the right. And if we want to turn to the left, so let's say this is 90, this is reduced to 70 or 60 or less than that. So it will turn to the left. So if you have very slow here, 20%, so you will have a sharp left turn, right? So that is how you control the movement of the robot using PWM, and of course using the motor speed. Okay, so that will be the PWM, and we will go to the last subtopic in this chapter, which is the programming technique. So this programming technique is actually what you have learned in computer programming, in C++ programming, in computer programming course. So to program or to write a program for a complex application that we have a very long line of code, uh, so we need to uh, to plan or to have very structured program where it is not only running line by line, where sometimes we need to jump to other location, right? Just like we learned in assembly that we use subroutine to for our more complicated program. So in this case, we use a function. It is actually the same as subroutine in assembly, where we will have the group of program that we can call anytime that when we want to use it, right? This is called a function. So for example, this is our main program. It's running like this. So at this point, we want to call a function or a subroutine in assembly language. So we call the function, so the microcontroller will go to this part of program, the function, run all the code in the function and return back to the main program after we finish all the operation here, right? That is called a function. So for example, in our program, uh, we can write a function to set the PWM duty cycle and period, right, using a function. So for example, we have the function called PWM set here, and when we use the function, we can write like this. Now we call the function PWM set, and we write this is value, this is value, this is called the parameter, and we can pass this parameter to the function, and in the function we call this as period, and see, this is how we actually uh, set the period of the PWM, right? So PWM dot period, yeah, period, so can be any value. In this case, if we run this, if we call this function, the value of this period is 0.010. If we call this, the value of period is 0.020. And this is how we set the duty cycle. Yeah, PWM duty cycle, and this duty cycle is flexible now. It is depend on this value. So this is function call, this is function call, right? And the function we need to define only one time here. So this is called the parameter passing. We pass the parameter or value to the function. All right. And we can see that our program is more structured and more easy uh, to write and to read, yeah, by using a function in writing the program. So in your mini project, hopefully I can see you apply the function, the use of function in your program. So I will share with you the rubric for the mini project. So to get a higher mark, one of the requirement is to use function in your programming, in your program. Right, means that you use the advanced, better programming technique to write your program. This is another example of using function to for the seven segment, yeah, for the 7 segment display. So you can have a look at this program. So this is how we write the program or the process, yeah, the flow, the design flow of how we write the code, compile the code until we get what we call the executable program or binary file that we can program our microcontroller. And that will end our chapter. And we have many exercises here. Okay, 23 exercises that you can try, right? So you can try this, and maybe next week we can discuss the answer for this exercise. And see you next week. Yeah, thank you.